This is the second lesson on graphing. In this lesson, we're going to go a little bit deeper to the topic of graphing, and we're going to go beyond polynomial functions and take a look at also rational functions. Those are the functions of the form y equals f of x over g of x, when you have a quotient of two polynomial functions. But before we get to those topics, I'd like to begin with this example on the screen. So you have some information about a function. Given the f prime, the first derivative sign chart, and also the f double prime, second derivative sign chart, the question is asking us to graph the function f of x. And all we really have to do here is to do a rough graph, because we don't know the actual data points. We're never going to know the y coordinates of these x values that are given here. This is x equals 0, this is x equals 4. So we cannot do a perfect graph, but we can still get the skeleton and the rough curvature of this graph, and let's begin. Okay, if you recall from the first derivative, we can get information about increasing or decreasing nature of the graph. So this function is decreasing here, decreasing and increasing afterwards. By looking at that, we can do a skeleton. Okay, this graph is going to be basically falling up to the point x equals 4, and it's going to be rising afterwards. Now, we don't know how high. Like some of you could do something like this, for instance. We don't have y coordinates, but this is the rough shape of the graph from the first derivative information. Based on the second derivative, what do we know? F double prime is positive on the first part. That means it's concave up. Then it is concave down. And then it's concave up again. So up, down, and up again. Now this has to fit in with the previous portion of the graph that we have, the skeleton. So let's see. Up to 0, it should be concave up. So let's say here's our 0 point, here's the point 2, and there's our 4. So up to 0, it needs to follow the skeleton, meaning it should be decreasing, but at the same time, it should be concave up. So decreasing and concave up. Get a graph like this. From 0 to 2, it should be decreasing based on our dotted line there. It's going downwards, but at the same time, it should be concave down. So just a subtle change there. From instead of up, I changed to down. After that point, everywhere after the point 2, this graph is going to be concave up, but we should still follow the pattern. The pattern was it has to decrease up to 4, increase afterwards, and at the same time being concave up during that interval. So I guess perhaps you already see what this is going to look like, following the dotted lines, but this time with a concave up curve. So there is our rough curve then for y equals f of x. This point here is an inflection point. That point here is an inflection point. Since concavity changed over those points. We also have a minimum, but there is no local maximum for this graph. Okay, the next thing I'd like to do is, before we go and look at the graphs of rational functions, there's one more topic that we need to discuss in this section, and that is finding the absolute maximum and the absolute minimum of a function. You know, we know how to find local max and local min. We take the derivative and set it equal to 0. And, you know, we do a sign chart. If you have a situation like this, you have a maximum, right? If you have a situation like this, at this point, you have a minimum. But this is asking more than a local max and min. In this subtopic, we're looking at an absolute max and min. So that would be like the highest point on a graph, for example. So that would be the absolute maximum. This would be a local maximum, but it is not the absolute max. This is a local min, but not the absolute min. This point right here is the absolute min. So over on the entire graph, the absolute highest and absolute lowest points are referred to as absolute max and min. Now there is a theorem of calculus that says if you have a continuous function over a closed interval, the absolute max and min are going to exist. If, on the other hand, you have an open interval, something like this, from negative infinity to infinity, an open interval, not a bounded interval from a to b. If you have a situation like that, there is no guarantee that absolute max and min would exist. Like here, there's an absolute minimum, but is there an absolute maximum? A point that you could put your finger on there and say, this is the absolute highest point on the entire graph. No, because these arrows means it keeps getting larger and larger. So in this situation, there is no absolute maximum. So typically when we ask you to find absolute max or min, we're going to give you a function, a continuous function, and we're going to give you an interval from A to B. So let's say this is A to B. And then we're going to say find the maximums, absolute max and min in that interval. Here's how we do it. First, you will still need to locate the critical points. So set f prime equal to 0 or find f prime is undefined. Second, we're going to evaluate the function at the critical points as well as at the endpoints of the interval. Why do we do that? Because you see, endpoints are candidates to give us absolute max or min points, but sometimes you can have a situation like this. So the absolute maximum point on the graph can also occur at a critical point. So we're going to evaluate the function at the critical points and at the endpoints. These are the suspicious points where you expect to find the absolute max or min. And the highest value you get from that process is your absolute max, and the lowest value you get is your absolute min. Let's take a look at an example. And I will do the second one on this page. F of x equals x cubed minus 12x. The interval is from 0 to 4. The question is, find the absolute max and min for this function. So let's begin. First, we're going to locate the critical points. Set f prime equal to 0 for that. So 3x squared is 12, x squared is 4, x is plus or minus 2. Here's the thing though. Look at this interval. We're trying to find the maximums within this interval. And negative 2 doesn't even lie in that interval, right? So from these critical points, the only one I'm going to select is the positive 2, because negative 2 is not in that interval. It cannot possibly be an absolute max or min. So look what I did here. I took the endpoints of the interval, as well as the critical points that line that given domain in that interval. And I'm going to plug each one into f of x. And then we're going to find the corresponding y coordinate. So let's see what we get. So if I substitute 0 for x, I'm going to get 0. Let me plug in 2. 2 to the third is 8 minus 12 times 2, or 24. So that will give me negative 16. And plug in a 4, you will have 64 minus 48. And that should be 16. So now look at your second column values. The absolute largest value you got there, 16. This is going to give you 4 comma 16 is your absolute max. And the absolute lowest number you get on the second column, that is going to give you, so 2 comma negative 16 is your absolute minimum for this function.